Hello, I'm Saba, and I'm a postgraduate researcher at University of Leeds. I work in Qadiri Research Group, where we cover a wide range of research areas related to particulate systems. The poster that I'm presenting here is on our work on impact breakage of needle-shaped or acicular crystals. As you know, particle breakage by impact takes place in a wide range of processes. There's been a lot of research on the breakage of equine-shaped particles, but for acicular particles, there's only a few breakage studies, and they only investigate failure under either compaction or a combination of shear and impact. So in this work, we have tried to address this gap. Here, for the first time, we make use of Malvern Pananalytical Morphology G3, which is essentially an optical microscope to characterize particle impact breakage. The microscope comes with a disperser in which particle breakage takes place. How it works is that the particles are placed in a sample well, and a pulse of pressurized air is injected from the top. The pressure for this air jet can be adjusted. The particles then get accelerated and start impacting the walls of the spool back and forth, and they break in this process. Then they fall and land on a glass slide beneath the dispersion chamber, where the optical unit takes 2D images of the dispersed particles. The images are then used to measure different particle sizes. In our work, we use acicular crystals of 3 different samples as shown here. We disperse the particles at 10 different pressures, which means 10 different impact velocities, to find their particle size distribution after dispersion. The method that G3 software uses for calculation of particle volumes usually results in an overestimation in case of acicular particles. So by considering some assumptions, we find the volume base size distributions using a different method. The details of the methods are shown in these 2 slides. Here's an example of the distribution curves. As you can see, the curves shift to the left with increase in dispersion pressure, which indicates an increase in the amount of produced debris. This is also evident in the images taken from the particles lying on the glass slide. These distributions are also developed for length and width of the particles, which allows us to have a comprehensive characterization of breakage for crystals of each sample. We can use the distribution curves to find the extent of breakage of the samples. As you can see here, the extent of breakage increases with increase in dispersion pressure, but for potassium phosphate particles, they don't break much because they're large and they barely get accelerated. This calculated extent of breakage, along with the impact velocity of the particles, which are calculated from CFD simulations, are used in Qadiri and Zhang's model to find the breakability of the particles. The slopes of the fitted lines here are the breakability indices for each sample. Here, at the highest pressures, benzothiazine particles show a different breakage behavior, so these 2 points are excluded from the calculations. In conclusion, this newly developed method can quantitatively determine the breakability of acicular particles using only a small amount of sample, which is a big advantage in cases where the sample is valuable. Thank you very much for listening.